It's started. Good morning and welcome to the DINRG session. I found this place difficult to locate, and I assume other people may have as well. As usual, we've got our IPR policy, also known as the Note Well. If you haven't seen it before, give it a look. It covers IRTF IPR rules. So for those who aren't familiar with it, our mailing list is here. We are not actively maintaining the wiki at this point, but past material is on it at that URL. And here's the agenda. So first off, welcome. Well, minutes, Jabber. We still need a Jabber scribe.
Anybody on Jabber?
We have a couple of people on Jabber. Two of them are going to be presenting. Looks like there are several people who.
Melinda, I can sit in the room and relay.
Okay, that's perfect. Thank you. Okay, this is. We've got a bunch of presentations, mostly related to identity, but not entirely, as well as some updates on work that's been presented here in the past. Yeah, do you want to, what's that?
No.
Okay, yeah, and if you're not aware of it, we've been accepted as a workshop at NDSS 2019. That's February in San Diego. The call for papers will be going out shortly. The deadline for submissions is going to be the 14th of December, which is about a month, a little bit over a month. And people who are interested can talk to us offline. Do you have anything else to say about that? Okay. So our understanding is, I misspelled David's name. David is stuck in traffic, we understand. So let's start with Colin and an update on distributed authenticated mapping.
Is this the microphone? Hello? Perfect. All right, so I am not Colin. I'm Jean-Luc, but Colin cannot make it today. It's okay. All right, so good morning. I'm Jean-Luc. I'm a PhD student at Berkeley, and I'm going to give a quick update on the distributed delegating mappings draft. Oh, yes, clicker would be awesome. Okay. Oh, that's kind of. Okay.
We're going to put in a different full screen mode.
Is there? I think there's a different mode.
Move the mouse over to that side and some things will appear in the full screen.
Yeah. Do you know which one it is? That was the one I hit.
Yeah, and normally you can.
Okay, got it. Yeah. Okay.
All right. Awesome. Okay. So for those of you who haven't seen one of these presentations in the past, I'm going to give a really, really brief recap. This draft addresses these key value mappings that you see almost everywhere on the internet. And the problem with a lot of these structures is that they rely on a central point of authority. So if you're trying to send a message to Colin over end-to-end encrypted messaging, you're going to be trusting a key directory to keep that mapping secure. And the issue is that the key directories or the DNS providers or the CAs can arbitrarily change the values that they are overseeing. And so the core of this draft is to take the common elements from all of these structures and to combine them into a data structure that keeps all of these mappings in one place. And then we leverage each of the parties that has a stake in keeping these mappings secure to power an underlying consensus layer that Giuliano and David are going to talk about in a little bit. So that's the basic structure of the draft. We take a look at the structure. Very simply at the top, there's a root key listing for different applications. There's a series of links to different tables with key value mappings. And in those tables, you can define these cells that define delegations. So for example, if I want Berkeley to maintain a set of domain zone files, then I'm going to delegate the ability to a key owned by Berkeley to manage those. And these tables kind of compose themselves recursively until you get down to leaf cells, which are value cells, where you can actually map to the actual zone file. So that's, the 5-second description of what the draft actually does. Now I want to go into some updates. Okay, updates. A couple things we changed. The first is we changed the prefix-only delegation, makes everything kind of simpler in the draft, and we noticed that for pretty much any scheme that you use for delegation, you can always really map it to this system. So that's what we did. For example, you can just reverse the order of domains to get a nice prefix delegation structure. Second thing we did is we simplified and updated the verification rules. So there are more details in the draft itself, but essentially if there are valid timestamps and the fields changed or signed by the parties authorized to change those fields, and the cell doesn't violate the prefix property, then it's a valid update and can be applied. Third thing we fleshed out is a bunch of security considerations, so discussions on how the system actually behaves in the face of several types of compromises. The nice thing is that because this is based on a consensus layer with a lot of nice security properties, those properties bubble up to the actual structure here. And finally, we introduced the notion of these table allowances. This gives a total upper bound on the size of delegation trees recursively, where you can just sum the number of leaf cells and the allowances you've given to delegations to stay underneath that boundary. And so this is important, and I want to talk about this for the rest of the time, because for the first time we made a change to the draft that deals with how we govern the structure itself, how we decide which entries are valid or invalid based on some sort of restrictions. So I want to talk about this governance issue because that's come up in several meetings in the past. So I think it'd be good to talk about it. Okay, governance. The nice thing about the structure right now is that it gives us a very clean separation of concerns. So on one hand, there's the generic structure safety, that's the delegation rules, the update rules, who can modify which cells, and the global consistency that every client looking at the structure will see the same value mappings. And that's handled by the consensus. And there's a very clean split between that and all of the nitty-gritty details, like which table should be in, or which entry should be in each table, and who actually gets to subset of the namespace, who gets the delegations, how do you remove cells, how do you renew cells. And the nice thing about that is we can always, in most cases, point to the one person who has the ability to make those decisions, which are the table authorities. And that's useful because there are a lot of real world systems that we already have to maintain these mappings that we don't need to recreate inside the structure. So this is very well and good, but there's one kind of side case that actually bridges the gap, which is kind of annoying, and that's the root key listing. And the issue is that it's content specific because each of the applications are rooted there, but there's no actual single authority that we can point to, like IANA, to say, okay, you need to modify or maintain who is actually in this listing. So this issue is not really solvable with the table authorities or a straight consensus. And so what we propose here is that we strengthen the idea of consensus with a voting system. And by doing so, we can lump in the root key listing administration with all of the safety measures that we're already taking with consensus. And so what is voting? I mean, it's pretty simple. It gives consensus knows the agency to actually make decisions on certain updates to the tree. So they can either vote for or against changes to the root key listing. And it's an explicit additional requirement because there are some consensus schemes like PBFT, for example, that don't actually have a voting system, right? So you can't actually do this with, classic consensus. The nice thing is that a lot of existing systems already have something like this built in. So SCP and slice infrastructures, they have quorums, which naturally kind of translate to this type of voting. And you have Bitcoin, you have their system for determining protocol changes that can actually be adapted to this and hard forks and stuff like that. So by using this, we can actually leverage that to actually govern the root key listing. And so there are kind of two things that you have to keep in mind when you're thinking about this, is that if you get a prospective root entry and it's from the Pirate Bay, some of you might, or some nodes might, be okay with this, but some nodes, say if they're run by Sony, probably wouldn't be okay with that. And so you can address this issue very simply by just voting on it. Nodes that disagree with, allowing the Pirate Bay into the root key listing can just vote against the new root. Nice thing is that you have a set of potential outcomes that come out of that. Either the vote succeeds, which means that although you disagreed with the actual application, you can't disagree with the fact that it was actually added to the listing in the first place. If the vote fails, the remaining structure actually isn't impacted because all of your mappings are still there. And if there's a very fundamental disagreement between large sets of nodes, that indicates that it's probably not a good idea that they should be trusting each other in consensus in the first place. So That might be an argument that part of the network should be split into different worlds. The second thing is that that consensus nodes really care about is resource usage. And the way we solve this is through the allowances by explicitly including a value in the request that each node will see. And so,
Can I ask a quick clarifying question?
yeah, go for it.
Is the only definition of voting majority?
No, it is not. So in SCP,
So you could have, for example, a single vote veto as one
yeah.
of the
Yeah, you could.
one of the possible semantics.
Yep.
Okay, thank
It
you.
all, yep. Okay, and so if Tor shows up with a prospective root entry and it wants 1 billion cells, you probably don't want to do that because some consensus nodes might not be able to handle it. And so what that forces Tor in this case to do is to find a large enough set of nodes that will actually support 1 billion cells, or to adjust its request so that a quorum or any sort of voting party can agree that that is a good idea to add it to the root key listing. All right, so that is it. I'm happy to take any more questions.
Thanks a lot, Jean-Luc. Do people have more questions?
Thank you. So just out of curiosity, where would you like to see this work go in the context of this research group?
Oh, me?
Yeah.
Yeah, so I think the next step here is that I think this is clearly a good idea that we spent time fleshing out, and we'd start to actually implement this in a meaningful way. So I think that's the next step. And if someone wants to start implementing it in parallel, that would be awesome.
Okay, thank you.
Okay, just for the remote attendees, so Jean-Luc plans on implementing it and is welcoming any other parties to do the same, and maybe look at interop in the future. Okay, cool. Thanks a lot. Thanks for bringing this work here. David, are you ready? Okay, cool.
My sincere apologies for some transport mishaps this morning. Okay, so I'm going to update you guys on just kind of a refresher on the Stellar Consensus Protocol draft. So if you remember, the motivation here is that we think there's a need for kind of like internet level consensus, right? So for example, let's say you want to atomically transact across completely incompatible or mutually distrustful systems. Like I want to pay you money, and in exchange, I want you to give me a domain name, for example. Or let's say you want to do what Jean-Luc was talking about, irrevocably delegate identifiers, or irrevocably for some certain period, right? Then having this kind of internet level consensus where everybody keeps everybody else honest and makes sure everybody obeys the rules is very useful. If you want to, say, verify public disclosure and timestamping of information, like let's say you want to build an IoT device and you're worried about getting strong-armed into signing compromised bootloader. So what you might want to say is, hey, my devices will only install bootloaders that have been publicly logged in some kind of like firmware transparency log, right? So all of these things are enabled if we have some kind of append-only log whose semantics are enforced by internet level consensus. Okay, so the model in which we propose to implement this, we're now calling a slice infrastructure. Actually, Giuliano coined this term. So basically, a slice infrastructure is a set of nodes, each of which selects a set of quorum slices that are sets of other nodes. And basically, a node should pick quorum slices that it believes are important enough or large enough to speak for the internet as a whole, right? And the idea is that we want these kind of dependencies to work transitively. So let's say that I pick Stanford and the IETF as my quorum slice, and you pick, Baidu, WeChat, and Alibaba as your quorum slice. And it turns out that, Alibaba and Stanford both include Google in their quorum slices. So kind of transitively, we both depend on Google. And so we want the consensus mechanism to make sure that we always stay in sync and never get forked from one another, right? As long as in this case, in this example, Google would need to be honest. And of course, you might want fault tolerance. So for fault tolerance, you would probably pick multiple quorum slices, any one of which were acceptable to you. So for example, you might say 4/5 of the FANG companies need to sign off on something before you believe that it's happened, right? The Facebook, Apple, Amazon, Netflix, Google. Or maybe more realistically, these are big companies that are probably running multiple servers. So maybe you want 3/4 of the servers belonging to each of these companies to sign off on things so that if they have downtime for individual servers, it's fine. So in this model, basically, if we let capital V be the set of all nodes, and for some node little v, we let Q of little v be the set of quorum slices decided by node little v, we can define a quorum to be a set of nodes that contains at least one slice belonging to each of its members, right? So this is kind of the key definition. This is a repeated slide from last time, but like if you don't get this, the whole talk won't make sense. So I want to kind of just work through this simple example to make sure we're all on the same page. Here, it's a very simple example where every node has only one quorum slice. And so I can draw the quorum slice by depicting it by an arrow from a node to all the other nodes that is chosen to be in its quorum slices, right? So, so in this case, for example, nodes V2, V3, and V4 all pick V2, V3, V4 as their quorum slice. And therefore, V2, V3, V4 is a quorum, right? Because it satisfies every member of that set. On the other hand, if you look at V1, V2, V3, well, that is a quorum slice chosen by V1. However, V1 is effectively saying, I'm only going to agree to something when V2 and V3 agree to it, and V2 and V3, by virtue of the quorum slices they chose, are saying, we're not going to agree to anything unless V4 agrees to it as well. So this is not a quorum. And the smallest quorum that includes V1 is actually the set of all 4 nodes in this example. And as you can see, there was a question earlier about, can you have veto semantics, right? And here, every node has, nodes V1, V2, and V3 all have veto semantics, right? So in a more realistic example, you would have maybe more quorum slices, but if it's extremely important that, for example, IANA be able to veto something, then you could configure your quorum slices such that IANA, or at least one of IANA's servers, in like every single one of your quorum slices. Okay, so the way this consensus protocol is going to work is that nodes are going to send messages and they're going to collect messages, and a node V is going to take action when the number of kind of identical messages, when the set of senders who all sent the same message reaches 2 important thresholds, right? So the first is quorum threshold. That means that every node in a quorum that you belong to has actually, including yourself, has actually transmitted a message, right? So they're all kind of in agreement with this message. Note that you have to belong to the quorum. You don't care about quorums that you don't belong to. And kind of intuitively, that's what makes this resist Sybil attacks, right? Because in you might have some weird node that creates a million fake Sybil nodes to try to mount some Sybil attack and claim that it's in a quorum with those. You don't care about that because you only care about the quorums that that include your quorum slices. The second threshold is blocking threshold. And we say that a set of senders reaches blocking threshold when they all send the same message M, and there's at least one node from each one of your quorum slices that has sent this message M. So this means that, assuming these nodes are honest, that there's, and don't contradict each other, that there's you will not be a member of any honest quorum that contradicts M, right? Because every one of your quorums is going to include one of your quorum slices, which is going to include one node that already contradicted, or that already said M, so it can't contradict M. Okay, so the main subroutine in this algorithm is this thing we call federated voting. This is basically a way to agree on a statement. So you start in some kind of uncommitted state, and then if there's some kind of abstract statement A, and this is a subroutine, so we're gonna fill in A with various values, and you decide that A is valid, you can vote for A. And then if the votes for A reach quorum threshold, then you decide that you've accepted A. Once you've accepted A, you kind of broadcast the fact you've accepted A. And when the set of nodes that have accepted A reaches quorum threshold, then you say you've confirmed A. And at that point, good things will happen. You can kind of count on, all the other nodes also confirming A. Conversely, you may have thought that not A was both A and not A were valid, and you may have just decided to vote for not A. That's okay. You can actually still accept A if there's a blocking threshold of nodes that also accepts A, right? And then you proceed to broadcast you've accepted A. Once that reaches quorum threshold, you've confirmed A, right? Now, two very important rules. You are not allowed to vote for two contradictory statements, and you're not allowed to accept two contradictory statements. But as you can see in the diagram, you can vote for one statement and then accept its contradiction if the contradiction reaches quorum threshold, and then you can go on to confirm that. Okay, so why do we like confirming? Well, first of all, if you have this property called intactness, if you are intact and you confirm a node, then all the other nodes that are intact are guaranteed eventually to confirm A. So intact essentially means that your quorum slices are good and there haven't been too many failures, and so this intuitively is useful for liveness. And then you also have this nice property that you won't, if nodes are intertwined, meaning if you delete all the bad nodes, if they still have quorum intersection, then two nodes will never confirm contradictory statements. So that, of course, is key to safety. All right. Now, the bad news is that you might start voting on some statement and not make it to the confirmed phase. And if that's the case, then you will not. You may get permanently stuck. So until you've reached confirmed, there's no guarantee that you'll ever resolve whether this statement is true or false. Okay, so let me now give an overview of the protocol kind of by phase. So you start in this nominate phase, and the goal is to pick some value to kind of try to agree on. So we run this nomination protocol, and nodes are likely, if the network has good timing and has is a synchronous network, like there's no network outage or long delays, then nodes will very likely all agree to nominate the same value or set of values. But it's not guaranteed, right? Because you can have hiccups in the network, and it's only probabilistic. So then the whole rest of the protocol is to kind of clean up the mess in case nominate didn't work out and converge by the time you decided it was over. So the first phase is prepare, and it really breaks down into two parts. In the first part, the goal is to confirm a statement or a set of statements, prepare B, for some ballot B. And a ballot is a pair that has an integer counter and a value, which is the thing you're trying to agree on. So a value would be like a set of updates to the Del Maps data structure that Jean-Luc was talking about, for example, right? Now, what is prepare? I said it's a set of statements. It's a set of votes. It's a set of votes to abort a whole bunch of ballots, namely every ballot B prime that's less than B but has a different value. And I'll illustrate this in a few slides. And kind of initially you take B dot value from the output of the nomination phase until such point as you've actually confirmed some ballot prepared, at which point you take the value from the highest confirmed prepared ballot. Now, if part one succeeds, then you've confirmed prepare B. So kind of part two of prepare is that the goal is to kind of vote and accept commit B, to actually commit that ballot, where commit and abort are opposite. So you can't vote to both commit and abort a ballot. So now you vote to commit this ballot B that's been confirmed prepared, and one of two things happens. You may fail, and in fact you may find out that even though you were hoping to commit B, that B has actually been aborted. You may accept the fact that B was aborted, in which case go back to step one. Otherwise, you proceed to the commit phase, where you broadcast the fact you've accepted commit B, and you now try to confirm that statement, right? And once you've confirmed that statement, you're done. You can decide on the value that is embedded in that ballot, and you also output an externalized message, but that message is kind of an optimization to help slow nodes like prune their quorum search when they're trying to figure out what happened while they were cut off from the network. Okay, so how much time do I have left? I think I'm running.
About 7 minutes.
7 minutes. Okay, so I'm going to gloss over some of this so I can get to this status. A ballot is basically, as I said, a pair of an integer and a value. The key invariant is that you cannot vote to commit a ballot B unless you first confirm that ballot is prepared. So here's kind of the nomination flow just quickly, you're kind of voting to nominate values. You never vote against nominating a value, so nomination actually never gets stuck. And what happens is you stop voting to confirm new values, stop voting to nominate new values as soon as you've confirmed one value nominated. So at that point, kind of the set of values that are in play gets frozen, and eventually they kind of trickle out in the background until everybody agrees on the same set of values that are nominated, and then you just need to combine them in a deterministic way. So if there are, for example, sets of transactions, you might take their union, and then that's guaranteed to be the same everywhere eventually, but the problem is you don't know when the nomination is finished, so you might say, okay, nomination's over prematurely, in which case different people will have different values. So then for the balloting, essentially what you do in the common case is that you you send this prepare message in the prepare phase to prepare a ballot. If that succeeds and you actually manage to accept the fact that that ballot is committed, then you vote to, you send a commit message, which is essentially confirming that commit vote, and then you're good. You can output that value. Now, if it doesn't work out because people came in with different ballots, different values in the first ballot, then you start over with a second ballot. And the protocol is kind of self-clocking in the sense that what happens is you set a timer when you're on a particular counter, but you only set that counter once you see a quorum also be at that counter. And then you bump your counter either when your timer expires or when you notice a blocking threshold of nodes is at a higher counter, because that means you've kind of fallen behind. And so that has the effect that the timer gets longer as the counter gets longer. And so if the network is partially synchronous, eventually you're going to spend longer and all the good nodes are going to spend longer and longer periods of time at the same counter, which is going to let them effectively emulate a synchronous protocol. I think Juliana will talk a little more about this. Okay, so just to kind of show an example here, initially here, let's say we're trying to decide between 8 values, A through H, and kind of here's all the ballots laid out in a grid. Let's say that initially you prepare 1, G, meaning you've confirmed all the lesser ballots as aborted, and then you vote to commit 1, G, but you might lose that vote, and you might accept that 1, G is aborted anyway, right? No problem, you bump the counter, and now let's say you prepare 2, F, and so now you vote to commit 2, F. Now, as I said, a vote can get stuck, so maybe that gets permanently stuck, and we'll never know, we'll kind of never agree whether 2, F was committed or aborted. That's okay, because we can still prepare 3, F, and if we succeed and then we vote to commit and then we confirm the commit of 3, F, then we know that the system has picked F. And you can see that the important point here is that all the stuck and all the committed ballots have the same value. And the definition of prepare is carefully crafted in such a way that even if there's a stuck ballot, you can still prepare higher numbered ballots as long as they have the same value. Okay, how's my time? 3 minutes? Okay.
Let's say 5.
Okay, so there's only kind of one really substantive change since the last draft, which is that there was a ballot that the people from MobileCoin pointed out really only needed to be a counter, and values are large. A ballot is a counter and a value, and the value is like 256 bits or larger. The counter can be very small, like 32 bits. So basically, we replaced this ballot, which is kind of like the accepted prepared ballot, the highest accepted prepared ballot, but that at a different value from prepared. But really, all you need to know is that below a certain counter, you've accepted all ballots as aborted. So that makes that shorter. So that was nice. We like shorter messages. The rules are basically that you set that A counter field based on the second highest or the accepted prepared ballot that is highest that has a different value. So you have to remember that, but it makes the messages smaller. Okay, so the important point is status. So basically we have kind of some good news and some bad news. The good news is, the draft I think is stabilizing. Like people have read it and started implementing it, asked a bunch of questions, but we've addressed those questions. And, if we're going with this protocol, it could be that we're very close to having something final. Some other good news, which maybe Juliana will touch on, is that it turns out that the existing protocol has slightly better liveness than we had initially proved. So we get that for free, but that doesn't mean we can't do better. And finally, the draft is actually having the intended effect that like people are out there are like reading the draft and actually implementing it. So now I'm aware of at least 4 different implementations, one of which is the original one in Stellar Core. Someone named Bob Glickstein has done one in Go. MobileCoin is implementing this in Rust. And Piers Poulsen, whose name unfortunately I misspelled here, sorry, maybe I can fix that, he's been active on the DINRG mailing list, and he's implementing that as well. Now, there's some bad news. The bad news is that we might either need other documents or like a huge change to this if we really want this to take off. The first problem is that there's no hope of interoperability between these implementations because the draft deliberately hasn't specified how the messages are multicast, right? And that's because we don't know what the right solution is, but we think that, I personally think that that's like an important thing that this research group might need to address because a lot of systems need this kind of end system multicast. In fact, if you look at a whole bunch of blockchains are doing this and they're doing it kind of in a bad way and it's not really very failure resistant. Some other kind of either good or bad news, depending on how you look at it, it turns out we can improve on the liveness, but it makes the protocol a little bit more complicated. So now we have this trade-off. Do we want to go with a new protocol that has extra stuff to have this increase in liveness in what might be kind of a corner case, but is maybe something you want? I'm not sure. Giuliano, I think we'll talk about this. And also there may be a simpler protocol for slice infrastructures. So maybe we just want to like junk this draft or have a competing draft or something. I'm not sure. So that's kind of where we are right now.
Okay, cool. Thanks a lot. Questions? So I had one. So is draft version 5 what's currently implemented in Stellar Core?
No, I went with the decision to try to make the thing as simple as possible instead of exactly documenting what's happening. And especially until we have a multicast layer specified, that seems to be important. So particularly the latest change wasn't implemented, and Stellar, there's like some repeated fields in Stellar that are like later in messages, and it was just cleaner to like move them out into like the message envelope. And I figured, since this is kind of a chance to start over, like we should do it cleanly. Okay. We at some point when this is fixed, we could like fix Stellar or.
Okay, what are your plans for addressing the multicast issue? That seems fairly
well, I'm not sure. So I'm also not aware. I highly suspect that there's stuff happening at the IETF that's like relevant to this, and that people here know more about this than I do. So ideally, if you know of like things that would be useful towards implementing as kind of standard end system multicast for these kinds of distributed systems, can you talk to me? I'd love to hear suggestions. If not, we can just go off and try to do something. To make it Byzantine fault tolerant and open is actually a fairly tricky problem. And Giuliano and I have been talking about that. It may be that we can leverage slice infrastructures to actually do what would be really hard without slices and actually have a robust Byzantine fault tolerant end system multicast algorithm, but we don't have one yet.
Dino.
Hi, this is Dino. Quick question on requirement for multicast. Will you provide your own reliability and just need datagram multicast, or do you want a reliable transport?
Yeah, we can have retransmissions, and the messages are all like, they're all datagrams.
So you do not need a reliable transport multicast protocol?
No,
okay.
No. But, well, it sort of needs to be reliable in that you don't want these so-called eclipse attacks where someone comes in, like if you want to attack Bitcoin, what you can do is like each node has like 8 outgoing connections and whatever, 200 some odd incoming. So you can basically monopolize the incoming, wait till you monopolize the outgoing, and then you can cut one mining pool off from the other mining pools. So
would your application just send UDP packets is the question?
Yeah, UDP is fine.
Okay, thank you.
Right, thanks.
Thanks for those questions. So I was thinking, so this multicast topic, that could be an excellent topic to follow on the mailing list or future meetings. So to figure out what are the requirements and maybe have some discussions what people think is actually applicable. Thanks again, David. And next is Giuliano. And you have your slides. Got them? Yes.
Hello. So my name is Giuliano. I'm a postdoctoral researcher at UCLA. And so I'm going to talk about the new results on the liveness properties of the stellar consensus protocol. So SCP should satisfy the safety and liveness properties of consensus. It's a consensus algorithm. So the safety properties are namely validity. So intertwined nodes must not externalize invalid values, where invalid is means the value is not well formed or does not pass application level validity checks, and also agreement, which means that intertwined nodes must never externalize different values. So as David said before, intertwined nodes are a set of well-behaved nodes that whose quorums all intersect. Now for liveness, what we want is that if we wait long enough, all intact nodes should externalize some value. So intact is another set of well-behaved nodes that I will describe a little bit later. So here you can see a table that shows what are the guarantees provided by SCP depending on what we assume about the system. So if we assume the system is purely asynchronous, meaning we have no idea how long it takes for a message to be delivered or what the clock skew between node is, then SCP can only guarantee safety. And in fact, this is not surprising because according to the famous FLP theorem, it is impossible to have both safety and liveness in an asynchronous system if a single node may fail by crashing. So assuming asynchrony is kind of strong. In a real system, we have some idea of what the message delay is or what the clock skew is at worst. But sometimes it's not accurate enough, and there are some periods where those bounds do not hold. So in theory, we model this with what we call eventual synchrony. So in eventual synchrony, we assume that initially the system is asynchronous. There are no bounds on message delay or clock skew, but it comes a time after which the system stabilizes, and now we have some bound on message delay and clock skew. So if we make this assumption, and we also assume that nodes fail only by crashing, then SCP guarantees safety and also liveness with probability 1 for the intact nodes. So what does this mean? Well, SCP is a probabilistic protocol where nodes use a random number generator to make some choices. And live with probability 1 means that as time advances, the probability that no intact node externalize a value goes to 0. Okay, so this is for crash stop failures only, but now if we assume that some nodes may be malicious, then things change, and in fact, SCP does not guarantee liveness. And this is what we're going to try to fix. Now, there is a third assumption that is in between both that we can make. So we can assume that eventually there are some malicious nodes in the system. Initially, there are some malicious nodes in the system, but after some point, the good nodes, they're able to detect them and they remove them from their slices. So they kick them out of the system, basically. And in this case, SCP still guarantees liveness with probability 1. Okay, so before delving into this case of malicious nodes, I want to say a few things about this intact set. So the intact set is a set of nodes for which it's possible to guarantee safety and liveness. And so in the SCP white paper, the set I was defined to be intact if after deleting its complement, V minus I became intertwined, meaning all its quorum intersect at good nodes. And also, I is on its own, in the original system, a quorum. Now, so we have a new result. Let's see it go on.
We're not plugged in.
Yeah. So we have a new result with a new definition of the intact set, which is better than the old one, in fact. So now a set I is intact if after deleting the malicious, the ill-behaved nodes, the set I is intertwined.
Keep going.
Yeah, okay. And also we require that the set I is a quorum on its own. So the set B of ill-behaved nodes may be in fact much smaller than the complement of I. And so in this case, the new intact set is bigger than the old one. So this is good because we realized that we can ensure safety and liveness for more nodes than we previously thought. Okay. And we also conjecture that this is optimal in the sense that no protocol can ensure safety and liveness for a larger set, but we haven't proved it yet. So now let's go back to liveness under eventual synchrony when there are some malicious nodes. And we'll start with the simpler case of crash stop nodes. So eventual synchrony is very nice because it gives you the ability to emulate a synchronous system. So here we have a synchronous system with 3 nodes. And so this is a closed system, like SCP for simplicity. And so we can slice time to synchronous rounds. And in each round, we know that every node will hear from every other. So in such a system, it's very easy to solve consensus. We can just ask the node to collect values and then decide on the maximum value they see, for example. Since all the nodes will see exactly the same values, they will all agree on what is the maximum, and we will solve consensus. And in fact, SCP is doing something similar, as David said earlier, not using the term round, but in fact, the ballot counters in SCP correspond to rounds, and the synchronization protocol is trying to emulate a synchronous system like this. So this is all fine if we don't have malicious nodes, but now if malicious nodes exist in the system, like this node N4 here in this figure, it doesn't work in the same way, because the malicious node does not have to play well in the synchronous round emulation. They can just not follow the round structure and send messages whenever they want. So here, for example, we have this node N4 that sends a message to N3 right before the end of the first round. Now, N3 tries to tell the other guys that there's a new value in the system, but his messages don't make it to the deadline that ends round 1. And so the nodes N1 and N2 will drop the message. So now, in round 2, N3 will start with a different set of values from N1 and N2. And so if we use the same rule as before, we might now disagree. Okay. So this is a problem it's easy to solve for safety, but for liveness it's actually tricky. And in SCP, a node like N4 cannot cause a safety violation like we see here, but it can delay the protocol forever. So there are some existing Byzantine fault-tolerant protocols that survive those kinds of attack. And so what is the classic solution? Well, it's to use leaders. So a protocol like PBFT, for example, associates a leader to every round and then ask the nodes to not accept any new value unless it's signed by the leader. So in our example of before, they would not accept, N3 would not accept the value of N4. Okay. And they also associate leaders round robin, meaning that every round has a different leader and we cycle among all the possible nodes, which will ensure that eventually we'll get a well-behaved leader and the system will terminate and produce a decision. So can we do the same thing in SCP? Well, in SCP, we cannot do round robin because we don't know who are the participants. So we cannot choose a leader round robin. So instead, we will use the nomination protocol to kind of emulate a leader. So the nomination protocol guarantees that all the intact nodes can agree on some value with non-zero probability. And so this is like having a leader that distributes a value to everybody and with non-zero probability succeeds in convincing everybody to adopt the same value. So the idea to fix the liveness problem of SCP is to run nomination protocol every time the ballot counter is increased. So this would give us a new protocol with a different phase diagram. So in the current SCP, we start with nomination once at the beginning, and then we never run nomination again, and we cycle between prepare and commit. Well, here instead, we will cycle between nomination, prepare, and commit at every ballot counter until we're able to externalize some value. Okay. Okay, so this is the proposed modification to SCP. But as we've seen before in the table, if we assume that the good nodes can eventually kick out the malicious nodes from their slices, SCP will terminate in the current implementation. So in practice, it's not clear that it's worth changing SCP and making it more complex to solve this liveness problem, and this has to be discussed. All right. So finally, to conclude, so we have some upcoming results. Streamlined theory of sliced infrastructures, including the new definition of intact. And also we have a new simpler consensus algorithm that might be interesting. I call it an algorithm and not a protocol because for now it's been analyzed in theory, but there's no implementation, and there might be some practical issues that we have not identified. So this concludes my talk. If you have any questions, please ask.
Yeah, that's really interesting. So where do you stand? I mean, what's your sense of whether or not you want to integrate these changes? Yeah, sorry to.
This is what I'm still hoping for is like a free lunch. Like, what would be great is if we could kind of map one protocol to the other, and that like this will be a way of kind of thinking about the protocols, but that on some level we can show them that they're equivalent and that it's just easier to think about it this way. So, but we'll have to. I guess I'm reserving judgment. It's true that people have not. That it is hard for people to understand SCP. It's a complicated protocol. So if we have one that's easier to understand, that would be better. And yeah, I don't know whether it's worth doing a separate draft for that, or maybe feeding something back into SCP, or finding a new way to explain SCP this way.
Excuse me. Okay, I will take this to the mailing list because this seems like sort of a fairly important question. So in terms of the updated consensus algorithm, have you started modeling that yet, or I mean, where does that stand?
Yeah, I get. So we don't have something ready to publish yet, but that's the next thing we should do, I guess.
Okay. Any questions?
Anjul Malhotra from Boston University. I have a question regarding nomination. How is the leader nominated? Is it
How what?
How is the leader nominated?
So
Do you have it in the draft?
probably don't have time to describe it right now, but it's
Okay.
it's a probabilistic algorithm where every node basically picks somebody from their slices and listens to what he's saying, and we can show that with some probability this will form a big tree rooted at a single node, and everybody will listen to this guy. I can describe it to you offline if you like.
So there's something pretty basic I'm struggling with.
Who are you?
Dave Ryan,
Yep.
Network Systems Research and Design. There's something really basic here now I'm struggling with.
Yeah.
Which is, if you in fact have a BFT agreement protocol,
Mhm.
I don't understand why you need all the rest of it. Why can't you just build consensus directly on top of a Byzantine agreement protocol if that protocol could scale?
Yeah,
I mean, most of the objections to adding BFT are scalability objections,
so-
right? Because the message complexity of many of the
So here-
existing BFT algorithms is quite high. So I'm actually struggling with what all the other complexity in SCP buys you once you add Byzantine fault tolerance.
Yes, so I mean, to me, Byzantine fault tolerant agreement and consensus are synonyms. So I don't know exactly what you mean by what is the difference to you?
Consensus is one semantic for agreement. You could have other semantics for agreement other than consensus.
Yes, so my view on this here is that, so we're trying to come up with a Byzantine agreement protocol, and there are different trade-offs that we need to make it scalable and performant. That's what we're trying to do.
Right, so Dave, you're going to answer my question.
Well, so I think that what this is trying. So I view consensus as kind of like a broader thing that includes like the Bitcoin proof of work. But Byzantine agreement has certain like properties that are better for a lot of applications. And so this is just, the slice infrastructure is the first model that can actually do Byzantine agreement and be resistant to Sybil attacks. So that's essentially what we're doing, is saying that, hey, instead of this proof of work stuff, if what we have is a situation where there's a bunch of known counterparties that you have trust in, and you think they're not all going to misbehave, but you can't, magically designate who are the tier 1 validators any more than you can have unanimous agreement over who's a tier 1 ISP, but you have kind of rough consensus, then this is like the first algorithm that actually works in that model.
Excuse me. Okay.
Okay, sure.
There's another way to think about it, which may or may not be better.
Okay.
Thank you.
Thank you very much.
Thanks, Giuliano. Quick question. Where are the blue sheets? There must be somewhere in the room. Okay, so who hasn't signed them? I think there were a couple of latecomers. Maybe just pass them around again. I think a couple of people coming late. All right, next is Alexander.
Morning, everyone. So I'm going to talk about something that's a little bit farther off from what you just heard. It's about namespaces in distributed ledgers. Apologies to those who have actually seen like a 5-minute talk about the DNS op. It sits a little bit between DINRG and DNS op. So that's why I'm actually talking in both groups about that. So this is shared work between myself, my colleague Dimitri Kresev, and Marco Sabatello, from a guy who is involved in decentralized identifier definition. So a little bit of background. I'm not sure whether it's actually necessary to explain that to you guys, but you probably know that distributed ledgers such as blockchains and similar infrastructure typically uses an address to identify a resource. So an address can look like a string that's in the slide below, and that leads to a couple of problems. Yeah, I mean, the first problem is interoperability. So that string doesn't actually reveal which ledger, which blockchain, which infrastructure it is. So I could actually go ahead and do trial and error on a couple of distributed ledger infrastructures and see whether any of those addresses is valid. Maybe some of those ledgers will not even reveal whether it's valid or not. And the example above, for example, is a Bitcoin address. And the second one is more like a usability problem. I hope you haven't seen something like on the top right, bottom right yet, but if you ever try to like actually pay to a Bitcoin address to get back your encrypted data, then you'll probably have realized that the addresses are actually really hard to type. They are impossible to remember. They feel a little bit like European IBAN numbers, but that's a different story. So the problem B is usability. So we're really bad at remembering addresses, and humans want names. So we need to solve those two problems, and solving problem one, interoperability, is you need to add identification of the ledger instance to the address. Only that qualifies it in a way so that you actually know where to use it. So that creates a unique and hopefully resolvable address. So in that case, you can say like, oh, pay me at the Bitcoin address, blah, which makes it pretty clear which ledger instance you're talking about. There's a different side problem now, because people actually need to agree that you can only allocate each identifier for a ledger instance just once, because otherwise you are back at square one. So there's actually work going on in the W3C credentials community group, and I've heard from Marcos that it's soon to be upgraded to a real working group, which means they can actually create W3C standards. And what they did, they went ahead and defined actually a URI scheme that solved this interoperability problem. It's currently a provisional registration with the URI scheme registry, and it's a hierarchical scheme. So the scheme prefix is DID for decentralized identifier. And under that, there's a set of methods. Each method like sort of refers to a distributed ledger infrastructure. For example, BTRC is for Bitcoin. And after that, there's a method-specific ID, which in that case is an encoded Bitcoin address. So that actually solves our problem, because if at least an engineer sees the ID column, BTRC column, blah, then they know how to resolve actually that address. It's still not really human readable. Yeah. So solving problem B, usability, we need to connect an unreadable address to a name. Yeah. And obviously the question is like, which names, which technology? We really want that name to be globally unique. We want it to be globally resolvable. And admit it, I'm a DNS person like everybody else in my company. So the obvious bite reflex sort of is like, let's put it into DNS. Yeah. So the DNS is a well-established infrastructure and blah, 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 blah. So, and we have been there like about 30 years ago to connect unreadable addresses to names. Yeah. So actually in most of the blockchain developments at some point started to consider including a naming service. So in almost all cases, they have some slide on their website or a graphic that shows like, oh no, you don't want to use the address, you want to use the name. So there's quite a rise of, I call them the on-chain naming service or naming schemes. And what's really an interesting surprise is that almost all of those schemes in some way follow the semantic structure of the DNS. So it's at label.label. Yeah. And that is a little bit two-sided to me. On one hand, I think that it's really a little bit lack of creativity, because if you invent a completely new infrastructure for the internet, then you would probably, at least on the topmost layer, you would at least need to like look into inventing a different type of naming scheme. On the other hand, it shows me that the DNS is probably so dominant in people's understanding that they simply go for what everybody's used to. It's maybe also user adoption concerns that people don't understand that it's supposed to name on the internet. There's one pioneering distributed ledger, which is Ethereum name service. They actually assign or auction off names under .eth, which is probably not the wisest suffix chosen, because it's also the three-letter country code for Ethiopia. So Namecoin was a little bit of a different thing, as you might remember. It took like the administration of the DNS onto a blockchain instance, but it didn't really address blockchain resources. It addressed normal internet resources. So a couple of example initiatives are EOS, NNS, IOV. None of these namespaces are really usable from the global DNS. And where sometimes even the structure of those names collides with identical DNS spaces, which in turn creates a confusion at the user level, because it depends on which app I use on my phone. I go to a different service, even if it's the same name. And that, in my opinion, differs the interoperability properties. So I would say if a blockchain defines a namespace, it should be impossible to create a collision with the DNS. Yeah. Because the DNS is so dominant that it's actually probably deferring the purpose in the first place. So we thought about, let's put it in the DNS. And if you have been watching the DNS space recently, there's like a lot of discussion usually about the so-called DNS camel. DNS is pretty much a complex protocol these days. It's like thousands of pages of RFCs. So we typically have on the right the poor overloaded DNS camel. In that case, it's not overloaded, but anyway. On the left side, we have new DNS work. And in the middle, we have sort of like part of the DNS community who says we need to defend the camel from new work. So with that in mind, we went back and said we want to do as little as possible actual protocol development to get that going. And so what we put in our draft, we used an existing DNS RR type, that's the URI RR type. We used, for the mapping from an email address to a DID, we used an existing experimental RFC that's called DANE for OpenBGP. So it transforms the email address into a hash and uses that hash as the owner name. And for the owner name of the DNS record we are trying to propose is, we are using an existing IANA registry. Yeah, there is a slight problem with that part because the policy of that registry doesn't really allow something that's not directly connected to a port number or transport protocol. And decentralized identifiers are not really connected to a transport protocol because they are some kind of abstract thing. So that string above is simply what we are proposing. So you have a DNS name, you add underscore DID as the label in front of it, and then you add an URI record or a URI record set that refers to a decentralized identifier, which in turn allows the client or the app to resolve that resource on whatever ledger or blockchain is specified in the DID. We do have running code. There's a DID resolver called UniResolver. It's sort of like the prototype resolver. It's on a web page. And you can actually enter a domain name under our labs infrastructure, and you get back a DID on the sovereign test network, and that then resolves to the public key of that network. So it's really simple. It's existing DNS technology. Essentially, it's available on each and every operating system out in the world, and connects sort of the world of decentralized identifiers with the globally resolvable DNS, and hopefully makes it easier to find resources on blockchains. Next steps. So my question sort of to the group is like, do people think this is useful? Have I missed another development in naming schemes on distributed ledgers? And if you wanted idea to proceed, please consider getting involved on the DNS ops discussions. Yeah, that's about it from my side. Yeah.
Oh, thank you. What's the status of the work in DNS ops? My understanding is this was the first time it was presented there. Is that correct? Is there an intention to ask for the work to be adopted?
Maybe next time. Maybe in Prague, yeah. So that's the way forward. I'm going to have a discussion with hopefully the transport area director, because they are responsible for the service name parameter registry, where the policy doesn't really allow something that's not connected to a protocol to be included in the registry.
Yeah, I actually have a question about that, but Dino?
This is Dino. I have two comments. First on interoperability and the second on naming. If we just write a spec that says what hash is used to generate the address, I think the blockchains can interoperate just fine. So that's just one comment. In terms of naming, I think it's useful but dangerous, because today when I look at a blockchain, I see these opaque addresses. That's a feature, not a bug. It just says somebody sent so many Bitcoins to somebody else. Could be somebody, could be a process, could be a service. The fact now that I have that data, and I hope you don't want to do reverse lookups, because then you're going to be able to tell me it's dino.com or something like that. So I'm not convinced it needs to go in a global database that anybody can look up and find Bitcoin addresses or any blockchain address. It sounds like it would be more secure and more private if we just use contact lists like we do on our phones. Now everybody gets their contact list out of sync, but my contact list is fine. I have addresses of people and nobody else knows what addresses I have. So I think the applications should just implement this independently and not have a global scale sort of design for this.
I think it depends on the use case. You're right. If I look at self-sovereign identity, I definitely don't want my identities, relations that I have with somebody included in the global DNS, because you mentioned reverse search. I would suppose that there would be some search engine thingy coming up. So even if we don't do the reverse, there will be some passive DNS infrastructure that actually exposes that. So I think if you connect a resource with the DNS, then it's essentially public. Yeah. But I'm always seeing like on almost all of the up and coming naming schemes, don't pay me at blah address, pay me at bank.whatever. Yeah. So it's more like people who want to
they certainly do that, but you can't then go look at their account and see how much was donated or whatever.
Right.
And this is what is being enabled with these payment systems.
Sure. Yeah.
Paul Hoffman, this is the DINRG, where we're talking actually not just about payment systems, and hopefully not at all about payment systems, but about distributed internet type stuff. If it's on the internet and you want it found, I would hope that you, in fact, would want it found, and you would want it found in an interoperable fashion. And so I think what Alexander is proposing here is exactly right. Using part of what we have now on the internet to help identify things on the internet. Now, the distributed part may or may not work. That might be a question, but saying I want to have something private that is an internet, facility just doesn't make any sense to me.
There's one side motivation on that. I think that the idea by itself is not really very sophisticated, but we actually wanted to prevent somebody coming up with something, trying to get a patent on it, and so it's more like an IPR thing as well. I'm speaking here so that if everybody wants to implement something like this, I want it to be an open and globally available solution, and not a patent owned by whatever private company. Yeah.
The other thing is that there's people need to support distributed applications as well, and those may have their own requirements around naming. Excuse me, I have one question, and that is that the structure of the DID looks a lot like a URN. Why did you choose to go with a new scheme rather than putting it into the URN namespace?
I'm not the right person to answer that, unfortunately, because I'm not involved in the DID development. But we simply discovered that there's ongoing work in that space. My initial intention would also be that a URN would probably be fine. Yeah, so the DID scheme could actually live under the URN space as well. But I think that's a question to ask to the W3C community group. Yeah.
Okay, thank you.
Thank you.
Thanks.
Oh, I'm stealing this.
Okay.
Right. We have now Nathan presenting from Singapore. Nathan, can you get in the queue? So you need to raise your hand in the Meet Echo browser window. Right? See you.
Hi, can everyone hear me?
Hi, Nathan. Can you hear us?
Yes, hi. Can you see me?
Can you move your mic a bit closer?
Yep, it's very close to my... Can you hear me now? Hello?
Yeah, not loud enough.
Not loud enough, is it? But you can hear me.
I think it's the AV system. Can we have the audio from the remote turned up, please?
Okay, hello. Perhaps it's the speaker. Is it the speaker? You can see me.
See you.
Try again.
Hello, test. Test.
Yeah, if you can just speak up a little bit, then it should be fine.
Sure. I'll speak a little bit louder. Okay, hi everyone. Very good morning to all. Okay, so this is Nathan, and today I'm going to share with everyone what are some of these interesting research issues that I'm working on. Okay, hope you can hear me. All right, let me just control. Can I control from my computer?
I'm afraid not. Just say next when you need to start again.
All right, next. Okay, so I wanted to start off this session with sharing some of the issues and constraints identified that have been identified with the use of decentralized identity. Okay, and in the area of my work, right? So so a little bit. Let me just do a quick summary: scalability, privacy protection, and interoperability. Pretty much some of the challenges have been shared by the previous speakers, and then some of these solutions, which I think could possibly be the key to solving these issues. For scalability, would be separate the consensus mechanism from execution, and probably having some private data on off-chain in secure enclaves. Secure enclaves is an area which is very exciting. A lot of people are working at it right now. Google Eslo, for example, and that Oasis Lab, this startup in US, really doing some exciting stuff with their Keystone enclave, right? And also privacy protection. Right? How can the right to be forgotten reconcile with immutability, which is often associated with decentralized platforms, right? So I look into zero knowledge set membership. This is one of the research that one of the big financial institution which has done. Right, very interesting there. And also interoperability. How can multiple decentralized identity platforms coexist together? Perhaps through the use of hash time lock contracts. The concept behind it. It doesn't have to be just for funds transfer. It could be again, for interoperability purposes. All right, next slide. Next slide.
Okay.
All right, next. Perhaps the next slide. Okay. Right. Okay. So, for I think everyone here would be an expert in this area. All right. So just let me do a quick sharing on the background, challenges, and constraints. All right. So, as we know on the internet, you can be nobody knows whether you are who you are and what's the problem statement. All right. There's a missing identity layer, which is why Facebook, LinkedIn, all of these platforms exist to fill that void, fill that missing void, right? All right. And then we can know that centralized systems, right, such as Facebook, Facebook has been hacked. So the solution that's often asked is whether is the solution a more secure centralized system? I think that's fool's errand, because systems have always been open to hacking and vulnerabilities. So perhaps not, why not explore decentralized identity or self-sovereign identity, SSI, right? This is something very interesting and an area which I've been looking into for the past 1 year. Okay, next slide. All right. So what is a digital identity? So it's a social construct with a context. That's important here, right? Everyone has a social construct, who you are, right, and the friends you have, right. For example, myself, Nathan. Now I'm a blockchain engineer with a bank in Singapore, right, and who others perceive you to be, a geek, for example. So some of these contexts could be the people around you, right, your family, your groups, the organizations which you belong to, and institutions. And perhaps most importantly, identity has an identifier context, right? And this is what the last speaker has spoken about using DIDs. Okay, next slide. All right, so for example, I have a Twitter handle. I also have a GitHub handle. All right, and someone could grant me an access, right? Perhaps using SEML, very popular protocol over here. And then how do people identify? The state identifies, for example, in Singapore through my NRIC, my passport, and my frequent flyer numbers and my hotel loyalty numbers. So pretty much, how one is identified is through these different mechanisms. So the question is, how can we strengthen our decentralized identity through all of this various, centralized identifiers repository. Right. Next slide. All right. So what problems are we trying to solve, or rather, what problems am I trying to solve and contribute to this community? Right. I realize that there's no standard that makes it easy for users to assert their verifiable qualifications to a service provider, right? So verifiable claims, very popular, right? For example, my loyalty card is this, and I have an account at bank, right? And I'm over the age of 21, right? And I'm a blockchain engineer, right? So there's no standard per se across many of these providers, right? And this has resulted in manual input, multiple manual input, and fraud. Next slide. Right, and so also another one is with existing attribute exchange architectures, right? OpenID Connect. Users and their verifiable claims do not independently exist from service providers. This means users can't easily change their service provider without losing or fragmenting their digital identity, right? So you have many islands of your digital identity sitting all around the islands, right? Facebook, LinkedIn, GitHub, and all of these things. What is the result? Vendor lock-in, identity fragility, duplication, confusion, and inaccuracy. And of course, reduce competition in the marketplace and reduce privacy for all stakeholders. Okay, next slide. Right, so in short, right, what is the pinpoint? Users cannot control their identities and information, leading to a lack of security, vendor lock-in, and industry-specific solutions. So perhaps at this point, I would like to share what are some of the things that the Singapore government is working on. The Singapore government is working on this thing called the National Digital Identity, of which I'm keenly watching this progress. So the government has plans. If any one of you have visited Singapore, you will see a trial machine, right, where your retina, where your fingerprints will be captured, along the customs, right? So the government is keeping our biometric information, storing our biometric information, and then using it as a form of identity, right? And this identity cuts across social service, for example, application for social aid and so on and so forth, right? So, and also at the same time, Singapore recently encountered a cyber hack where our healthcare records were hacked, right? So this is a really pertinent issue, identity. How do we secure identities, right, in all these centralized repositories? So this is an area where many challenges abound. However, at the same time, constraints means opportunities, right? So I'll talk more about this later on in the next slide, right? Next slide. Okay, so decentralized identifiers, again, it was mentioned just now, right? I won't talk about the history, everyone knows about it. And we have this DID, right? DID, Sovereign, DID, Indie, DID, UPort. So I'm on the ERC 725 Alliance. I look into Ethereum-based blockchain identity. I've used UPort before. And then I'm going to show you a quick demo later on, not really a demo, or rather a link which you can access to get your hands, dirty on this decentralized identifier concept. But are there many challenges? There are, and I'm going to talk about it. Okay. Next slide. All right, okay, so this is a DID document. All right, as we know, the DID identifier sits on the blockchain, different blockchains, Sovereign, perhaps Ethereum, the public Ethereum, and so on and so forth, right? And then it resolves to a DID document where you can see these DID documents will point to service endpoints, right? Where it will be a repository of your information. So I can imagine a landscape where I have my own DID, right, which is stored on perhaps Ethereum. And then it points to this endpoint, the Singapore government repository, for example, right, where it contains my biometric information, my retina, my retina information, right? So this is how it should look like, but are we moving? I'm going to talk about how we can possibly move to a semi-public-private infrastructure architecture, right, for our identity stores, our identity repositories. All right, next slide. Okay, so this is how a DID looks like. The scheme, the method, which is the blockchain platform, and then of course the method specific identifier. I think what is interesting is there's this triangle, they call it the Zuki triangle, where you can't have something which is meaningful, sort of a cap theorem, right, for identity, right, where you can't have something which is meaningful and at the same time easily remembered and unique at the same time. So there are significant trade-offs in this area of work, right? So again, a very interesting research topic. How can we transform this so that people like my parents, my grandparents could use it, right? Okay, next slide. Right, so again, this definition, a claim is an assertion made about a subject, right? And credentials, a set or more claims made by an issuer, right? Perhaps the Singapore government, right? And of course, the verification process, and then the decentralized identifier, DID, that does not require a centralized registration authority because it is registered with a distributed ledger technology or other form of decentralized network. It will be interesting to see how decentralized platforms, blockchain, for example, could work hand in hand vis-a-vis centralized repositories such as the Singapore Government Identification Repository. All right, next slide. Okay, so what are the connections between verifiable claims and DID? Right, a DID can exist without verification. Today, I can have a DID on Ethereum, and verifiable credentials are identifier agnostic, meaning these credentials are not tied to a particular identifier, right? But verifiable claims can, right? These claims that can verify a DID, right? Whether Nathan Au, right, owns this DID, right? And the combination can afford certain things such as cryptographic security via Hyperledger, and so on and so forth. All right, next slide. All right, so DID infrastructure can be thought as a global key value database. Hyperledger perhaps uses CouchDB or LevelDB, right? And it's all DID compatible, right? And what is in the DID document? The DID, the cryptographic material, the public keys, your public keys, private keys, and the protocols, and the service endpoints for interaction with a subject, timestamps, and JSON linked data signature, right? Next slide. Okay, so this is the very high level of how this ecosystem will look like, how you will work. You have your issuer, right? Could be LinkedIn, Facebook, GitHub, right? And then it issues credentials, and then the holder acquires stores, and then you will present to the verifier, right? This is the process. This is a step where zero knowledge proof might probably come in, right? Because very often we talk about the challenges where how can we ensure that our data is not privy to others, right? And this is where ZKP, zero knowledge proofs, will really come in handy. And of course, the identifier registry, right, where it maintains all the identifiers. All right. Next slide. Okay, so this is interesting. So this is an ERC 725 demo implementation. So I work closely with the Origin protocol folks to discuss how we can advance decentralized identity on the Ethereum platform. However, this is only just one of the platforms that I'm experimenting on. Hyperledger indeed being the next one of the platforms that really interests me. Okay, so I will recommend everyone to hit out the URL, try out the URL, and add your identifier. Perhaps not really add your identifier. If you want to, it's a private net. It's a private test net. So not to worry, it's not on the public Ethereum chain. Right, where you can add your identity, your claim insurers, and claim checkers. Right, really fun. All right, next slide. Okay, so I think some of the areas which I'm doing some research on right now is exploring the usage of secure enclaves to enable privacy protection. Right, Google Eslo, very extremely promising. One of the open source enclaves framework which allows secure enclaves to be achieved, right? So this is certainly an area which I believe will be incorporated to decentralized platform in the years to come. So encourage everyone, to work alongside me and some of my peers, right, to advance how enclaves could be leveraged for privacy preserving capabilities. Right. Next slide. All right. Also, zero knowledge proofs. How ZKPs can be leveraged to limit exposure of our PII during the process of attestation, right? Thereby achieving GDPR. So, in the industry which I'm in, a lot of challenges comes from storing customer data. How do we secure the customer data, right? Be it centralized database or decentralized platform. And ZKP is certainly an area which many financial institutions are looking at, right? So I would also like to share with you the ING Bank recently, just last month, came out with this paper, which is zero knowledge ZKSM, right? Zero knowledge set membership. They came up with this research idea, right, where the prover could prove something, without and the verifier can verify it without knowing what the prover has, right? So I'm thinking of incorporating this into decentralized identity platforms. Of course, it's a work in progress, but again, would like everyone to really explore, go deep into this area. All right, next slide. All right, so again, going back to these issues and constraints identified, right? Scalability, I know it's a bit of a stretch. How can we put 7 billion people identity onto any permission decentralized platforms? And of course, privacy protection and interoperability, right? All of these issues, very, very pertinent issues for any decentralized platforms to really gain mass adoption, right? And again, I think it's interesting that all of us are here today and really looking forward to how we can collaborate on these issues. All right, next slide. All right, that's it. That's for me. Any questions and anything?
Thank you very much.
Would love to be there with all you guys, but work caught up. Great.
Okay.
Any questions?
Yes. Shigeru Suzuki, Keio University. Thank you very much for the good presentation. My question is the very last page of the slide, one page back, under the last statement. How do you want to use the hash time lock contract for the?
Okay. So this is very interesting. So I'm leveraging some of these concepts which I've learned in the financial sector, right? In Singapore, the central bank, MAS, right, is doing. They have this project called Project Ubin, where they they have embarked on the decentralized platform solutions for the real-time gross RTGS, we call it, right? Central bank systems, where it shifts money, right, from banks to banks, right? So we are exploring the use of hash time locks to perform fund transfer across different platform technology, different decentralized platform technologies. So the concept, even though, right, is limited currently to funds transfer, but I believe personally that this concept could help connect the different decentralized platforms together, right? Sovereign DIDs. How do we resolve DIDs, right? How do we do single sign-on, for example, across different platforms, right? So some of these hash time lock concepts could be leveraged, even though it is somewhat, at first glance, it is two-phase commit, right? It is a value transfer. It might not be pertinent to decentralized identity, but I believe that it holds some of these clues, some of these ideas, right, to making different blockchains, different DIDs on different blockchains speak together, right, connect together.
Yeah, I'm just curious that I understand the context of the two-phase commit, like inter-blockchain thing. And I was curious that what kind of identity you're going to swap, exchange. So.
Oh, perhaps it might not be identity, but there's this use case which we are exploring, where there's a single sign-on. Currently, we have a lot of these single sign-on platforms, right, where you sign in and all your identity is synced across different islands, right, in an organization, like a traditionally Active Directory. So could we perhaps leverage HTLC, for example, to perform a single sign-on across multiple blockchain platform, right? Because your DIDs could be sitting on different islands, right? So again, extremely high level, might not result in anything, but that's the direction where myself and some of my peers are looking at.
Okay, thank you very much.
Okay.
Any other questions?
I don't see any right now. So let's follow up on the main list. Thanks again, Nathan. Have a nice day.
Yep.
Yeah, bye. Okay, next up is Alastair Berg, and he's also really from remote. I'm getting you on. Yes. Probably F5. Oh, that's not F5.
Any PowerPoint users can give me a quick way to how to go into slideshow mode?
Sure.
Present.
Present.
Got it. Thank you.
So, Alistair, can you hear us? We can't hear you. So you have to get into the queue. So kind of click or, yeah, right. Here we go.
Okay. Oh, this looks like I could be on.
Welcome.
All right. Well, good morning, everyone. Hello from Melbourne, Australia. So first of all, thanks to Melinda Shaw for inviting me today to speak to you as you're all in Bangkok. So I spoke to the IAB in September, I believe, about some of the work that I've been doing with a few members of the Hub. So Melinda first contacted me after reading some of the working papers I've written on the economics of identity, along with a few other researchers. So I'm largely going to be talking about that work, and I'll largely be talking about self-sovereign identity. So first of all, a little bit about me. So my name is Alastair Berg. I work for the Blockchain Innovation Hub at RMIT University in Melbourne. So I'm a researcher. I'm also a PhD student. So about the Hub, we are a social science research centre. So we're primarily economists, but we also have legal scholars and digital ethnographers and other social scientists. But we explore the economic, the social, and the political consequences of blockchain and distributed ledger technology. And the conclusions that we're largely reaching is that they're an institutional technology, and we really think that they're going to change as well as compete with firms markets and governments. So we look at a few different, I guess, use cases you could consider them as. So we look at things like supply chains, we could look at civil society, we look at governance more generally, but we also look at identity, which is I'll be talking about today. So next slide, please. So this is what I'll be talking about today. So first, I'm going to briefly introduce institutional crypto economics, which is the school of thought that we're developing. I'm then going to talk about identity as a pretty peculiar and interesting economic good. And then I'll talk about the way that identity is used in contracting and exchange more general. I'll then broadly talk about what I see as the current state of identity, sort of where we're sitting today, and how I think we got here as well. And then I'll move on to self-sovereign identity, and hopefully lead into a brief discussion about the importance of identity technologies and institutions in sort of a wider societal and economic and political context. So next slide, please. Briefly about institutional crypto economics. So we think that blockchains are really significant because if nothing else, they prove or they are a proof of concept for a form of economic governance that we didn't know was previously possible. So we now know that it's possible to run a decentralized ledger, so a ledger spread across a dispersed computer network without the need for any central authority in charge. And it turns out that ledgers are one of the most fundamental economic technologies that we've ever seen. So usually as economists, we don't really pay a lot of attention to ledgers. We've traditionally thought of them as a fairly boring and dull tool used in the context of accounting, stock management and auditing and that sort of thing. But in fact, ledger technologies are really, really fundamental. So here you can see up on the screen a relationship between ledger technology and the institutional makeup of an economy or of a society. So first off, we can see writing and simple bookkeeping leads to far-flung trade and early empires. We then see double-entry bookkeeping leading to early capitalism.
Your last 30 minutes.
More complex forms of what you might consider.
So 30 seconds, not 20 minutes.
Alistair, it's Dan York. I did the job described. The Meet Echo folks are advising to perhaps turn off your video right now.
Oh, okay, sure. I will quickly look and see how do I do that. Oh, here we go. This looks like.
There we go.
There we go. Sorry about that. I'm not sure how long I was I was not visible to you, but I'll sort of keep pushing on, and hopefully it'll make sense to you. So, just returning to this slide, we can see here the relationship between ledger technology and the institutional makeup of an economy. So, writing and simple bookkeeping leads to far-flung trade and also early empires and kingdoms. Double-entry bookkeeping, introduced in Italy in the 14th and 15th century, leads to early capitalism, and then even more complex forms of what you might consider empire capitalism as whole classes of bureaucrats emerge to service these ledgers. And then, of course, digital ledgers lead to global financial capitalism and the sort of the world that we live in today. And then now, after 2008 and 2009, we see a type of ledger that we didn't really think was possible. In fact, we thought was impossible. Next slide, please. So after Bitcoin, we now know that money can be thought as a ledger of ownership. So indeed, much of what governments do is actually manage ledgers. So we have ledgers of property titles. We have ledgers of taxation obligations, entitlements. We can even consider citizenship as a ledger of rights and obligations towards and sort of derived from a nation state. But of course, firms are ledgers as well. So firms are networks of contracts and capital arranged in a way that produces economic stuff, so economic goods, widgets, and what have you. So you can imagine a firm as a list of relationship which maps who works in what department, who's got responsibility for what production, which machines and production inputs are owned, where to get more of them, and how inputs move through a firm to become stuff which you can then sell to other people and firms. So that's a ledger. A firm is a ledger, or really it's a complex network of ledger, but you can consider it from a ledger-centric view. So We use the economic theories of a few Nobel laureates, including Oliver Williamson, who built on the work of Ronald Coase and Douglas North. So Oliver Williamson, who won a Nobel in 2009, we believe that this is the ideal theoretical framework to understand the blockchain. So what Williamson was primarily interested in is understanding the make or buy decision that firms resolve. So is it better to buy stuff on the open market, inputs on the open market, or produce them yourself, so produce them in-house? And this choice fundamentally defines how big a firm should be and the incentives faced by corporate decision makers. And blockchains are really interesting because what blockchains do is they substantially eliminate what we call opportunism. So, and they do this by being a trustless technology. So we think for many industries, the blockchain is going to radically redefine the boundaries of the firm, potentially allowing individuals to trade talents and skills more freely outside of hierarchical constructs like firms. So a key determinant of the limit of the firm is this opportunism, or what Williamson described as self-interest seeking with guile, which is a key component of human behaviour. So in short, institutional cryptoeconomics studies economic, social and political structures in the light of these new types of ledgers, so distributed, decentralized ledger technologies, as basically blockchains. So next slide, please. So we think identity is a really interesting good, if you can consider it as a good. So one quick working definition for identity so identity and identity technologies, they basically allow heterogeneous agents to distinguish between other agents and also distinguish between various types of goods and services, and also money in order to contract or exchange. Now, I've got quite a bit up on the screen and I'm not going to go through all of it. I'll sort of let you have a look through yourself, but identity is really peculiar, and it's a peculiar type of good because not only do you produce identity information about yourself, so you go to university, you get a degree, you build up your reputation by doing good things, but others produce identity information about you as well, and often without your knowledge. So you can consider your reputation, for instance. So of course you can directly influence it by doing good things or by doing bad things, but of course so can others. And of course there are often inaccuracies built up about you via reputation. Next slide, please. So I'll talk about how identity is used and why it is such a fundamental thing in everything that we do. So identity is primarily a means of coordination. So the absence of identity information would likely completely stifle and prevent exchange and all forms of contracting. So you might buy flowers from the side of the road without any identity technology being involved. But any time gap between trade and settlement requires a promise. So identification forms a key part of all but the least sophisticated economic and political transactions. So who are we transacting with? How do we know they are who they say that they are? So this is what identity does. This is what it is. So participating in markets and social and political exchange requires that you prove who you are. So any time you make a promise, promises require that you provide a proof of who you are in order that fulfillment of a promise can be followed through at a later time. There's no contractual arrangements without identification. So more complex or significant transactions demand more formal identification of the parties involved. Identity is necessary for credit markets, and intellectual property has an identity function. Of course, banks and insurers need to recognize customers with whom they have an existing relationship and obligations as well. So governments also need to recognise voters to confirm that they have the right to vote, and recognise recipients of social security to confirm their entitlements. Governments seek to identify taxpayers to verify that they pay what is owed. So to grossly simplify, we see identity as having two broad purposes. One is to facilitate economic exchange. while the other facilitates exchange in the political realm. And to facilitate these types of exchange, we see in the historical record the emergence of identity technologies. So they might be as simple as surnames, passports, driver's license, and what have you. Identity technologies also function to dictate the size of markets. So consider just a humble name. So names are one of the most simple means of distinguishing between two individuals. They can basically be considered universal, and they provide a robust means for indirect interaction. Heritable surnames serve both commercial and state-based interests, and they're also a means to enforce inheritance, and they can also act as a tool of the state to enforce actions against particular ethnic or familial groups, while also ensuring obligations and entitlements are limited to those eligible. At the same time, or similarly, the development of the passport and other simple identification technologies is associated with early modern states imposing formal identity in the process of the state claiming a monopoly on the legitimate means of movement. And of course, formal identification also becomes very, very necessary when nation states bring in social security entitlements. Next slide, please. So we can see that identity has public good attributes. So as a public good, it can be provided a variety of ways. And the means of provision actually can affect the quantity of the good provided. So public goods can be undersupplied due to things like free riding, or oversupplied due to rent seeking and knowledge problems. In addition, identity also has properties of a co-produced good, as I mentioned before, where you can have identity produced by traditional producers, as well as what is known as consumer producers. So we see government production of production of identity services as being supplemented by subjective identities as emphasised by individuals. So these subjective identities might share some common characteristics with the uniform identity issued by the state, so like a name, for instance. But the variety of identities individuals themselves have provides far greater nuance and malleability than which can be provided by a driver's license. And from this, we can actually derive two theses. So the first one is that as an individual, we want a variety of identities for subjectivist and privacy reasons. The second thesis is governments want individuals to basically have one uniform identity and no more than one uniform identity. So thesis one describes the incommensurable preferences about the quantity and quality of the public good of identity provided. And thesis two suggests that there is an oversupply of identity. And through government monopolization of identity provisioning, as well as technological barriers, we can see the situation today where we so often bundle identity attributes and use them as part of exchange. So this oversupply of identity information is most clearly illustrated in the situation in the past when we go to a bar. So in order to prove just one attribute.
Last 15 seconds, could you repeat that?
Oh, I'm sorry. So through the government monopolization of identity provisioning, as well as technological barriers, we can see the situation today where we so often identity attributes and use them as part of exchange. So this oversupply of identity information is most clearly illustrated in the situations many of us would have had when we go to a bar or a club or a restaurant. So in order to prove one attribute about ourselves, we need to provide something like a driver's license, which contains a whole lot of superfluous information, which we don't need in that particular exchange. Where in reality, all the bouncer or the bartender or whoever needs to know is, am I older than 18? Yes or no, or whatever the drinking age happens to be in that jurisdiction. And talking about minimal attributes and then moving beyond the bar example I've just given, means that you also want to contextualize your multiple coexisting identities for privacy reasons. So your work identity, your social identity, your family identity, the identity that you use while participating in a hobby, They don't always overlap, and there's clear reasons why you wouldn't want them to overlap and you want to keep them separate. So, for instance, a borrower wants to prove and allow lenders to verify their credit and property holdings, but you don't want to provide any more information than is necessary. And this is in stark contrast to state-based interest in identity, which suggests that for reasons of state legibility and efficiency, an individual should have one and no more than one legal identity against which taxation obligations, welfare benefits, and voting rights can be managed. And it is also technological limitations that have led to this point. So we've not previously had a way to prove directly an attribute to a counterparty, short of producing some tamper-proof physical artifact or directly contacting the institution that issued some credential to confirm its authenticity. Next slide, please. So, of course, identity institutions are subject to technological change. So, for instance, literacy rates and norms about record keeping were technologies that facilitated the increasingly prevalent instances of birth records. The increased instances of digitization of commercial and government sectors, these may also have some real impact on how identity is managed in the future. So the future that I'm talking about now is the future where identity is cryptographically secured, decentralized, giving individuals ownership as well as graduated permission and control over many identity attributes. So the blockchain and the invention of the blockchain 10 years ago may provide the foundations for a future in which individuals have greater control over their identity and related attributes, rather than relying on the actions and perhaps more importantly, the cooperation of some state authority or some monopolistic commercial actor. So blockchains and of course other allied technologies and sort of work in standards that some of your other speakers have been talking about before allow for probabilistic certainty that a specific individual is the owner of a given attribute, while preventing third parties from necessarily correlating links between transactions and hence relating them to a particular individual. So asymmetric cryptography ensures that verifying entities are able to cheaply verify identity attribute claims, but are unable to alter them. And with allied technologies such as zero-knowledge proofs, it may also become possible to verify the existence and correctness of a claim without ever sharing the nature of that claim with the verifying entity. So of course we can see, and I'm sure that this is all very familiar to you, but we can see some of the main characteristics of self-sovereign identity, which of course has been written about at some length by those starting with Christopher Allen, Devin Lafretto, and many others, of course. And it also goes without saying all the work that people like yourselves are doing on work on things like decentralized identifiers, verifiable claims, by many other groups, including the W3C. Next slide, please. So what does this mean for the future? So in short, well, I'm patiently waiting for software engineers and computer scientists to continue the very hard work that you're doing on the technology and the standards that will truly put the individual at the center of identity administration, and one which emphasizes context dependence and individual control rather than administrative necessity, in the words of Doc Searls. But I'm also really excited about this because I think it may fundamentally change the privacy equation as well as the way in which many markets work. So first, privacy and surveillance. So storing your own attributes signed by some institution and simply sending that claim to whoever needs it allows you to prove some identity attribute without someone checking in with the institution issued the claim. So this fundamentally reduces the big brother problem and the capacity for state or corporate surveillance, which I think is really exciting. But the second and I think is worth considering is the new organizational forms which might emerge. So blockchain-based identity solutions may fundamentally allow counterparties to reduce the information asymmetry between them, while at the same time increasing privacy. So this obviously sounds counterintuitive, but when you consider the use of things like DID infrastructure, which can in essence create single-use identifiers, along with privacy-enhancing technologies like zero-knowledge proofs, we may be able to share more relevant information with fewer privacy implications, as malicious hackers can no longer target large honeypots of information. And I think this may even disrupt sectors, including the banking sector. So a transaction cost theory of the firm suggests that institutions such as banks basically amalgamate groups of lenders into one organization due to transaction costs and what I think of as identity cost economizing. So identity technologies like government-issued identification, as well as income statements and credit reports, they're basically expensive to collect, verify, and use to coordinate commercial lending and financial activity. The reason banks exist is banks economize on these costs. This is one of the most fundamental reasons why we have retail banks. Vertical integration to save on such identity costs is also, of course, dependent on the identity technologies available. So new ways to coordinate economic activity and costlessly, or at least at much reduced costs, verify identity information passed on by counterparties may actually cause such economies of scale to disappear. So we could see the banking sector and other what I call trust institutions become less and less necessary for complex economic and financial interaction. And I'm just looking up at my time, and it looks like I'm bang on time. So I'll move on to the next slide if that's all right, and I'll ask any questions. And I do understand that I had some internet problems, so I'm sorry that not all of that went through, but hopefully most of that came through. And if there are any questions, I'm of course happy to take them.
Thank you, Alistair. It was mostly fine for some glitches. There's one question.
Sure.
Yes, hi. Dejan Bogdanovic. Could you go please a few slides back where he's talking about the centralized, that's current model of identity versus the self-sovereign identity. You were showing, these attributes of that. And these are very nice goals to achieve. The biggest problem, and what we know today for some of them, is the economic, from the economist point of view, from the economic point of view, is why they should let you self-sovereign your identity, because by having your identity control, they are extracting economic value out of that. And there isn't a way how to, at least we don't know how to extract the economic value out of you when you are self-sovereign, when you're self-governing your identity.
Yeah, I mean, of course, and that's sort of the million-dollar question, especially when you consider, services which we use every day, like Facebook and Twitter and LinkedIn and Google, because of course they extract the value from us. So in many ways, we are the product, which is that well-used phrase. And
government as well. Sorry to interrupt, but government as well.
Yeah, indeed. So, I mean, any sort of large institution like governments and like these large corporate entities, I mean, they're certainly not going to roll over and accept us doing what they have done for us for the last 1,000 years. Again, I don't have a clean answer for you, apart from the fact that as more and more private organizations build these self-sovereign identity platforms and people are motivated to use them, through the publicity of large-scale hacks like we've seen so much over the last few years, then perhaps it might change their business model. I also see a large role for privacy regulations like the GDPR. So you'll notice, well, we're on the right side, as you can see. A lot of the characteristics of self-sovereign identity align quite well with privacy regulations like the GDPR. So things like control and transparency, consent, minimalization. I mean, they're almost the same requirements of the GDPR. So I don't really have a good, clean answer for you. But I think things like new privacy regulations, people's understanding of how our data is used by companies and governments may see a shift.
Okay, well, thank you very much.
All right. Thank you very much for having me.
Have a nice day. Bye.
Yeah.
Okay.
And that's it.
All right. In DINRG, in the last meetings we've had, we have largely seen maybe three types of topics. So maybe number one could be, called principles or concepts, so like digital identity, self-sovereign identity. Number two could perhaps be called, say, infrastructure, things like Stellar, delegated mapping, chain space, Coconut, these things. And topic number three, largely application ideas, so decentralized RPKI, so topics we discussed last time, not too much today. So we would also like to get a bit of feedback from the group. So what do you think about, say, the current, say, setting the current topics? Is there anything you would suggest we should do more? Do you have ideas for technologies that should be, maybe invited to DINRG? So maybe think about it. If there's anything that comes to mind, share your thoughts on the mailing list. Keep watching for the announcement for the NDSS workshop. So this will largely be a DIN event, but with the added feature that you can actually publish papers there. So we'll send out the corporate papers, I guess, this week. Thanks for coming. Have a nice day.
Also, do we have both questions?
I have one here.
If somebody knows where the second blue sheet is, forward it on.
So I'm from NOMCOM. We try to.
Hi, how are you?
Next time it might be earlier.
I'm also a chair next to you.
Thank you. Yeah,
okay. Yeah, thanks again. Okay. One more.
And you have a step activity trying to. So